Now, magnetic field. What is a magnetic field? Let's start from the magnetic field of the Earth. Here's a question. How does the Earth, where does the Earth get its magnetic field? This is the Earth core. The Earth core is made of, we say, liquid metal, mostly iron. Okay, it's iron. The Earth core got two layers. The inner core is a solid. Okay, and then the outer core is molten metal, we say, or you can think of it as liquid metal. Mostly iron. Okay, it's all iron. Okay, I will say here liquid iron. It consists of a lot of electrons moving. Mind the words, a lot of electron moving. And when you have electron moving, what happens? You have current, right? Because current is the flow of charge. Inside the liquid metal, there's a lot of electron flowing, and that produces a current. There's a current produced inside the Earth core. Now, when you have current and magnet, they are very closely related. Whenever you have electric field or current, you will have magnetic field. Here, if you are asked, where does the Earth get its magnetic field? How do we answer? We say that the magnetic field of the Earth comes from the moving charges in the outer core. Here, magnetic field comes from where? Comes from moving charges. Not stationary charges, it's moving charges, okay? So because of the Earth rotation and the liquid metal is constantly moving, you have moving charges, you have current, and then you have magnetic field. You can think of it like the dynamo, bicycle dynamo. The bicycle dynamo, when you pedal, right, there's a magnet inside the dynamo, right? When you pedal, the magnet inside spins, and then you have magnetic field. And then the magnet spins, it will create electricity. And then it will turn into light. That's how you get the light, right? This one, what is happening inside the Earth is the reverse of dynamo. It's like the dynamo in reverse, okay? So at first you have current, moving charges, moving electron inside. Then the current produces the magnetic field, right? Dynamo is from magnetic field go to this one, but how the Earth generates the magnetic field is like the dynamo in reverse, okay? So at first we have moving charges and then we have magnetic field. In very short, simple words, how does magnetic field produce? You answer this one. Enough, okay? Moving charges. Now, this is one way of producing magnetic field. Another type of magnetic field, okay, is from where? We know that a permanent magnet also has magnetic field, right? But what makes a magnet a magnet? Okay, what is so special about a magnet? Why some object has magnetic field? Why some object does not have magnetic field? Okay, see, we have understood already the magnetic field is created by moving charges, right? So if I take a magnet here, north, south, we know that it has magnetic field. So what creates this field? Again, it is moving charges. So are you suggesting, maybe you ask, are you suggesting that this magnet is a moving charge? Because it has magnetic field, right? Answer is yes. Magnet is actually made of moving charges. Magnet is just a general term, right? But the real reason why it has magnetic field is because of inside the magnet. Okay, if we zoom inside the magnet, you look at the electron inside the magnet. What happened to the electron inside the magnet? Electron, they orbit, right? They move in orbit. Then we have orbital motion of the electron. The electron is constantly moving. This orbital motion of every single electron, it depends on whether they are aligned or they are not aligned. Again, if you look at two electrons, let's say you have this electron orbit like this. This is the motion of the electron like this. Okay, let's say it's clockwise. And then you have another electron go in this direction. This is opposite motion, right? So opposite motion of the electron, they cancel out. That means the magnetic field get cancelled out, right? You have moving charges, but then if the two electrons orbit the opposite way, then they get cancelled out. So objects that are not magnet, they are electron inside, the orbital motion all cancel out. So it does not produce magnetic field. Okay? What makes a magnet is because inside the magnet, the electron, the charges, they have a net orbital motion, we say. Or I say that the orbital motion, they do not get cancelled out. Their motion is aligned. Their motion is aligned, in line with each other. Some electron, maybe they cancel out, but overall, net, they align. Okay, so I will represent the diagram, one electron as one arrow, like this. This is one electron. You can think of the electron as a tiny little magnet. This electron, like this, they all align like this. One electron is a tiny little magnet. If you have many tiny little magnets add up together, you get a big magnet. You get a magnetic field. The magnetic field becomes significant. So again, we come to the same idea. Where does this get its magnetic field? Get it from moving charges. Is the electron moving here inside? Yes, electron is also moving. Not necessarily it must move from left to right. It can move in orbit. It can move like this, right? That is also a motion of the charges that create magnetic field, right? So that is the first thing, the origin of the magnetic field. Now, we know that gravitational field, how is it created? Mass, right? Mass creates gravity, gravitational field. Okay, then what about electric field? How is it created? A charge or a stationary charge creates electric field. What about magnetic field? Okay, you now know a moving charge. Okay, create a magnetic field. The Earth magnetic field is created by a moving charge. Now, what is the use of Earth magnetic field? Is there any use of it? Yes, of course. Helps you in navigation, protect you from radiation. If it's not because of the Earth magnetic field, the Earth will lose its atmosphere, right? Because this is the Earth, here's the sun. The sun, from time to time, it will send out a burst of hot gas. We call it the solar flare. Okay, the solar flare comes here. If not because of the magnetic field that is holding the atmosphere together, when the solar flare comes, it can wash away the atmosphere. That means your atmosphere will disappear. This is what happened in Mars. Mars, they do not have liquid iron inside. So they do not have magnetic field as strong as the Earth. So when the solar flare comes, what happened? It washed away the atmosphere of the Mars. So the Mars does not have atmosphere, the Earth has. And it is kept protected by the magnetic field. Okay, so this is just general, just to give you like the use of it. Okay. Now, next one we look at, we now know how is it created and what is it. Now we want to look at who experienced this one. Who will experience magnetic field? If you look at gravitational field, is it everybody can experience? We say that everybody that has mass will experience. If you have no mass, you will not experience gravitational field. Electric field, everybody that has a charge will experience. If you put a neutral object, it will not experience the force. A magnetic field, who will experience? You must have a moving charge. Only it will experience the magnetic force. Okay, a moving charge. That means if you have a magnetic field here, then I put a charge here. Okay, this is the charge. It's a stationary charge. Sorry, this one you cannot see. I put it here. It is a stationary charge. Will the charge experience a force? This is magnetic field. We use a symbol for magnetic field, B. B, that is the magnetic field. Okay, I put the charge here. Can it experience any force if this is stationary? No, because only a moving charge will experience it. If this one moves, then you will start to see a force act on the charge. Okay, so that is something to take note. So two keynote I will write down here. First thing is that understand that magnetic field is produced either by moving charge or permanent magnet. Okay, that's the first one. Number two, who experience magnetic force? A moving charge will experience a magnetic force. In a magnetic field. Okay, now take a bar magnet here. This is the field lines. How do you draw the field lines? First criteria, you cannot intersect. Line cannot touch other line. Second, the line forms a closed loop. What does it mean? That means if you're asked to label inside, how do you label inside? Here, the arrow comes out from N, goes to S, and then comes in like this. Okay, it forms a closed loop like this. Here, and then go in. Same here. Go out, go in. Criteria number 3, the closer the spacing, okay, the closer the line is to each other, the stronger will be the field at that point. If you compare here and you compare with over here, this one you got closer lines. The spacing is smaller, right? The spacing is smaller. The lines are closer. So stronger field here, weaker field here, like this. Okay? Because you will be asked to draw the field lines. Okay. Of course, this one you know from north to south. North to south. Now, if I put a compass, the compass has a needle, right? The needle is a magnetic, is a small tiny magnet at the needle. If I put a compass here, where will the compass point? The compass will always follow the field lines. here, it will follow the field lines like this. I put it here, the compass, it will follow the field line. I put it here, it will follow the field lines. Here, field lines. That means whenever you put it, wherever you put it, this one will always point, follow the field line, which is towards the south, right? It points to the south. Now here's a question. Why the compass points to the south, but people say that the compass always points to the north? Here, you see, follow here, points to south, but isn't it always points to the North Pole? The reason is because the Earth magnetic field, you think of the Earth as a magnet, tilted slightly to the one side, okay, like this. Here, this is the south, this is the north. The Earth is like an inverted magnet. This is the Earth. Where is the North Pole of the Earth? Up here, right? Here is North Pole. Here is South Pole. This one, we call it the geographic north. Okay, geographic north. But then, geographic north is actually the South Pole of the magnet. So we say that the geographic North Pole is actually the magnetic south. Here is magnetic south. So how does the field line look like? Okay, the field line goes like this, okay, like this, like this. Now, here, all the lines point up. So if you put a compass here, where will the compass point? Again, follow the field lines, right? Follow the field lines. So this go up, this go up. You put it here, this go up. Where is it pointing? The compass is pointing to the magnetic south, or it is pointing to the geographic North Pole. So what people is saying is this one. The magnet always point to North Pole. Okay, that is, they are referring to the geographic North Pole, but it is actually pointing to the magnetic south. Okay, why like this? Because back then, okay, there was no clear understanding of magnetic field. So after they have declared this is North Pole, this is South Pole, then only they found that it is actually the other way around. But then they did not change anything, they just keep it like this. So like this. Right? Now, in this part, again, we will look at the field lines of a few different, the field lines of a permanent magnet. Okay, you have already, you should be able to sketch this one. Okay, and then also the field lines of an electromagnet. Okay, what is an electromagnet? If you were asked to define it, very simply, electromagnet. Electron is electric, right? Magnet is magnetic field. So the magnetic field is created by electric. What is electric? Moving charge. So electromagnet is referring to any object that is creating its magnetic field using the moving charge. Okay, magnetic field created by moving charge. And usually this is used to describe the current in a conductor. The current in a conductor. A conductor here is referring to wire. Okay, a conductor here is referring to the wire. Just think of it as wire. So current in a wire. Current in a conductor. Okay, so current in a conductor, you have moving charge, you have magnetic field. So even a straight wire, we call it electromagnet. Okay, we call it electromagnet because magnetic field created by moving charge. Okay, now How does the field lines of a moving charge? Let's say we have a conductor like this. Okay, current flowing up like this. Okay, you have a wire. The field lines, first you have a moving charge, right? So moving charge create what? Magnetic field. All right, so how does the magnetic field look like? This one, very easy. You use your right hand grip. Your thumb is going to be the charge direction. This one is the positive charge direction. Again, positive charge because current is the flow of positive. If it's negative, you have to reverse everything. So going up, and then you close your fingers, right? When you close your finger, that is the magnetic field. Okay, so if I see from the top, I see from the top here. What do I see? This is the wire. If I see from the top, then you see this. Okay, you see the cross section. That is the circle. So I will draw a circle here, top view. Top view, you have a circle. Then the current is where? Going towards my eye. Is going towards my eye. Towards my eye, you take your thumb, you point. The thumb is the current, right? You point towards your eye. You see the tip of the thumb is a dot. So that is a dot like this. If I see from the bottom, I see the cross section. Again, this is bottom. Current is moving away from my eye. Away from my eye, I will point my thumb away from my eye. What do you see? At the base of my thumb, here, if you have noticed, this is an X. Okay, the crease of my hand or the fold of my hand looks like an X. So if the current flowing away from you, you will see an X here. This is an X. Okay, so this one out of the page into the page. Okay, the lines like this. Going up, close it. This is the magnetic field. This one going in and then like this. This is the magnetic field. 3D, this is never just one. This happened across the length. Here, 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 here. Across the length, the entire length. And also, there are concentric circles. Okay, one circle, another circle, another circle. Concentric circle. What does it mean by concentric? The circle that share the same center. Okay, I draw another circle here. This circle has the same center, They are concentric. Okay, now that is for a straight wires. Now, if I take this wire, I make a circle like this. This is the straight wire, right? I make a circle like this. Then what do I get? I no longer get straight wire. Okay, we call this straight wire. If I make it like this, then I have a coil. We call it a flat coil. Okay, a flat coil. I can make a few turns. I can make more than one turn. I can make 1,000, 100 turns. But it's going to be a flat. That means if you see from the side, there is no length. Not like this, huh? Not like this. Like this. This one, you have a length. This is a solenoid. We will come to that later. All right. So if I make everything together like this, okay, then we get a flat coil. A flat coil like this. Okay. So the magnetic field of a flat coil like this. Okay, current flow from here to here. Okay, then you do grid going up, curve. Then here is in this direction. Here going down, and then you curve. Here you get a clockwise direction. Okay, so here, this is the coil. The current is flowing. How? Going from here to here. Okay, current is flowing from here to here. So if you focus the magnetic field around here, like this small little ring around here, it is this one here. Small little ring around here, this one. Okay, along the length here, you have the magnetic field like this. Okay, all around the ring. You have to think of it 3-dimension. Okay, for the magnetic field, in the study of magnetic field, everything is 3-dimension. So here, this is like this. So here you have a look. The magnetic field of this one, imagine you have a ring around it, and then the ring sweep around this loop. Okay, this is the magnetic field of this one. Right, so here you have also, here you have everywhere you have. Now, this is the magnetic field of a what? Flat coil, right? So if you look from above, top view here, this is we will draw the conductor first, the wire. Okay, this is the cross section of the wire going up. This is the current. Okay, here the current go into the cardboard. If I see from the top, the current go inside. This is a X like this. Then my view look like this. In the middle, how do you draw here? See this same direction. In the middle, we will draw a straight line like this. And I will do one more, like curve like this. Okay. This is top view, from the top view. This is 3D isometric view. Okay, here. Next one. The magnetic field line of a solenoid. Okay. I take a core like this, and then I wrap the wire like this. Then I get what? This is a solenoid. Okay. The difference between a solenoid and this one is that the solenoid has a length. Every single coil is separated by a distance. Okay, so this is like a rod, something like that. Here, this one. Okay. Here we have a solenoid. Now, how do I draw the magnetic field? Can we use the right-hand grip? What is the right-hand grip again? This is the current direction. This is the field, right? If I apply this on this one, isn't it difficult? Because you have coil, the current go out from here and then go back, go out, go back. Like you have every single different flow of current at every corner. It's very difficult to apply this. So we will use a different application of the right-hand grip. How is it different? We will switch these two. This is current, this is field, right? We can switch it also. I can make this one as the field, this as the current. I apply here. Again, this one I make it the field direction. And this is the current direction. I switch position, right? I switch it, and then I apply here. Now, depending on how the current flow, let's say the current flow like this. Go up, go to the back, go up. Go to the back, go up, like this. What you want to focus is that the current at the coil here. Okay, if the diagram is not labeled for you, then you have to label the current at the coil first. After you label, then you use this one again. This is current, so you coil it like this. Okay, you coil it like this. And what is this again? This is field. Field direction is pointing like this. Okay, so if the field direction is pointing here, what is the polarity over here? This is north, this is south. Okay, the field is pointing here. Recall back our magnet. The magnetic field line is a closed loop from north to south, and then come back. You see what's inside? The inside is like this. So when I use my thumb, okay, coil, and then my thumb is pointing, follow the field here. This is the field direction. Okay. To put it simply, you can just think of your thumb is always pointing to the North Pole. It is always pointing to the North Pole. Yeah. Now here, this is the magnetic field, and then we also have this. Okay. Comes out here, curve, and then go back. Then what about in the inside? How does the magnetic field look like inside? Inside the coil is where you will get uniform magnetic field. That means all the lines, they are parallel. Okay. Inside, they are all parallel. So we get uniform magnetic field. This is a very nice setting of the solenoid. The advantage is that a solenoid, they give us uniform field. Uniform field. Okay. What is uniform field? Same, they experience the same force everywhere in the uniform field. Okay, so you have how many types? Straight wire, flat coil, and then a solenoid. These three, will be asked in the CIE. Okay, here, these three are considered electromagnet. Now, we will look at the solenoid. If we put a core inside, if we put an iron core, it will strengthen the magnetic field. We call it here, if I put a ferrous core. What is ferrous? Ferrous is iron. Okay, this is iron. I put an iron core, then it will strengthen the magnet. How and why? Why? How come I put a core inside and then it will strengthen the current? The magnetic field. Okay, the reason is because like this. Let me get some space here. Okay. Now, first thing is that the iron core. Remember earlier I said what makes a magnet a magnet? This is a material. If the electron orbit does not align, okay, these are the electrons, they are all disoriented, they do not align. One rotation, one motion cancel out the other one. They have no magnetic field. Okay, this is what 99% of the object in the physical world, right? For a magnet, they all align like this. Okay, for a magnet, they align like this. Now for iron, if we put iron core inside, at first the iron core is not magnet. They are like this one. If I put inside here, this one will become this one. Because of the magnetic field of the solenoid. Again, okay? If I put the iron inside here, the magnetic field of the solenoid, not the iron, the magnetic field of the solenoid, the red one, will make the iron from here to here. It will make the iron from here to here. This process is called magnetization. Okay, magnetization. We say that the iron core has been magnetized like this. Okay, so if the iron core become this one, what happened? This one is a magnet already, so it has field. It has field. If the iron core become this one, it has field. That means the iron core now has field, and the field is added to the field of the solenoid. Now you have extra field like this. Okay, you have extra field. You have the field from the iron core, you have the field from the solenoid. If you have more field, what we discussed earlier, smaller spacing, stronger. If you have more field, smaller spacing, stronger here. Okay, so we say here, why we add a ferrous core, it increase the strength, because iron core add magnetic field. And magnetic field. Due to it being magnetized. Okay, that's the first one. Number two is also because of, if I put a core, let's say this is the field, okay? This is the magnetic field. If I put a core inside, in the middle, I put a core in the middle, how will the core change the magnetic field? The magnetic field will look like this. Okay, so here I put a core. What is the core doing to the magnetic field line? The core bring the magnetic field line together like this. Okay, they bring them together. So they concentrate. The lines, the field lines. Okay, they concentrate the lines. Oh, you cannot see it. Let me. Okay, they concentrate the lines. That means they try to bring as many lines as possible together. Sometimes some lines will be too far away. Too far away, that means they are wasted. You did not utilize all of the line. Some magnetic field line, they are too far away, so they are wasted. That we call it a leakage, a magnetic field leakage. So this core bring the line together, so they concentrate the lines. So you minimize the leakage of the field lines. Okay. There's a term, they call it the minimize flux leakage. Okay, minimize the flux leakage. Flux is the lines. These two, okay? So why this one make it stronger? This one and this one. This one and this one. Okay. Magnetization is electron lining up. Okay, the motion of the electron lining up. That is the magnetization. All right, let's go to the next one. Force on a current carrying conductors. Okay, suppose that we have a magnetic field. Now, please do not get confused between magnetic field and the current. If I draw magnetic field, there's no circle. I draw like this, X, X, X. Okay, this is a magnetic field because there's no circle like this. If I circle it, then that is current. Okay, if no circle, then that is magnetic field. Right, so this is the magnetic field. What is the direction of the magnetic field? It's into the page, right? Into the page. Wait. Oh, someone just had a power cut. Okay, never mind, we'll continue. All right. Okay, so we have a magnetic field into the page, right? So the way you think about, okay, you think of it 3D, right? So you're looking from your screen. This is the field, okay? It's going like this. It's going like this, huh? Okay. Now, I put a wire here. Okay, a wire, or we call it a conductor. There's current flowing in the conductor. Now, let's recall back. Who experienced a magnetic force? A moving charge. Not a charge, it's a moving charge. A moving charge experienced a magnetic force. So if you have current flowing, okay, you put a wire inside a magnetic field, the current is flowing, the charge is moving. That means the charge will experience the magnetic force. If I focus on one charge, just one electron here, this electron is moving, this electron will experience the force. Okay, and the force applied on every single electron in the wire. If you have 10 million electrons, then all 10 million experience the force. That become a net force. Now, the electron experience the force, right? The electron is inside the particle. The electron is inside the particle of the conductor. So if the electron experiences the force, then the particle experiences the force. Then the conductor experiences the force. That's why we call it force on a current carrying conductor, right? So force applied on electron, it applied on the conductor as well. So when you put the wire inside the field, there is a force being applied on this conductor. Where is the direction of the force? We can find it using your left hand rule. Okay, not right hand, is left hand. Okay, this is field. That is the index field, right? This is the current, and this is the force directions. Now make sure when you use this hand, you make sure all 90 degree. This one is 90 degree, this one is 90 degree. And open wide, don't do like this. Okay, like this, you cannot see anything, right? So open wide, and then you need to use your wrist to help you. Okay, when you align the magnetic field and current, don't move your finger, move your wrist. Okay, move your wrist. Now, here the magnetic field inside. So I'm going to point like this inside, the current up. So I'm going to move again. I move my wrist. I twist my wrist. Okay, not like this. When you move, when you align this one and this one, don't forget the first one that you have aligned. Okay, some students, they never get the right direction. Why? Because after they align the first one, then they align the second one, they forgot the first one should be pointing to the board. Okay, so when you align the second one, remember the first one has to keep in that way. Okay, if you change it, then you will never get the correct directions, right? So this one like this. Now the force is left side. Okay, that is the force on the conductor. In the previous physics, in your O level, we are only asked to identify the direction, right? We are never asked to calculate what is the force. But in your A level physics, here we will quantize this one. We will quantify this force. How much is the force is actually acting on this conductor? Okay, we will look at one formula, the magnitude of the force here. Magnitude of force is, okay, what is the formula? BIL sine theta. This formula we will not look at the derivation, but there's another formula later. We'll look at the derivation of that one, because we don't need to deal with differentiation, the mathematics behind it. Here, what is this B? Okay, now we have come to magnetic flux density. Magnetic flux density. What is I? Current, okay? I is current. L is what? L is the length here. The length of the wire inside the field, inside the field. If your wire stretch like this is your wire stretch outside. Then what is the length I get? I only take here to here, okay? The length that is inside the field. That is the L. Okay, sine theta. Sine theta, this is the, like this. If this is my field, magnetic field, B, okay? Pointing to the right, like this. The wire, I put like this, I. Or I can put like this, I. Right? Okay, that is the magnetic field. It is going to, okay, imagine that this space is all magnetic field going like this. Put my wire like this. I can also like this. Okay, like this. This wire and the magnetic field, they are on the same plane. Same plane. What does it mean? Here, if I take a piece of paper, this is the magnetic field, B. And then the wire is on the same plane like this, I. They are on the same plane, they are on the piece of paper. Okay, they are on the same plane, they are on the piece of paper. So this angle here, I put theta, this one. It is the angle between these two that is on the same plane. Like this. Okay, like this. Right? If I'm going too fast, let me know. Huh? If I'm going too fast, let me know. Okay, so that is the okay. Later, the calculation part will come to that later. Okay. Okay, now that is the data. If my conductor is like this, okay, it's like this. Okay, that is my magnetic field. My conductor is straight. That means what? They are making what angle? They are making 90 degree. 90-degree angle. If 90 degree, sine 90 is 1. That means this one become F equals to BIL. Okay. If this one, I twist it and it become parallel like this. Okay, the wire, I twist it, become parallel to this one. Then the angle it makes is 0. Okay, 0 here. If angle is 0, then F equals to 0. What does this tell you? If the field like this, your wire is like this. This is the field. This is the current direction. Going there or going here, doesn't matter. As long as they are parallel, then there will be no force experience. Okay? Only if like this. This is the field. Okay? This is the field. This is the current. Like this. Right? Here, no. Then what is this? Maximum. Okay? Perpendicular is maximum. Decrease, 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 decrease until 0. Again, here, that is the field. That's the wire. Maximum force experience. Decrease, the force decreases. Like this, decrease, and then become 0. Okay? So when is the maximum? This is the maximum. The maximum force applied. This is the force applied on where? On the wire, okay? Not on the electron, it's on the wire. F is the total force, this one, on the wire. Okay, that is the angle. In the formula, take note of the angle. The second one, you will look at the B, magnetic flux density. Okay, what is this? Sounds so complicated. Okay, very easy. You just think of it as your magnetic field strength. Remember your gravitational field strength? W equals to mg. Okay, what is the G? This is G equals to W over M. That is the Newton/kg. This is gravitational field strength. Gravitational field strength. A measure of how strong is the field. How do you measure it? They define it as how many Newton acting on 1 kg. Because if I ask you, how strong is the field? Let's say this one was never created. And then I ask you, how do you measure the field is strong or not? Like, what do you use to compare whether the field is strong or not? Is this field stronger or that one stronger? If you say, okay, I put an object here, and this one fly that much. I put another object here, this one fly this much. Okay, this one move this much. Then what I'm using to measure the strength is how far they can fly. Right? That's a quantity I choose to measure. Because I'm measuring the strength based on how far this one can travel, how far this one can travel. So I'm measuring the strength based on how far it has traveled. But they define that how strong is measured by how much force per kg. Okay, how much force per kg. That is the gravitational field strength. For the magnetic flux density, this is like magnetic field strength. Think of it like magnetic field strength. Okay, it's just a technical word here. Okay, think of it like this, but never use this. Okay, don't write this in your book. You write this in your book. Okay, in the exam. This is like this one. Okay, so it is a measure of how strong is the magnetic field. Just like this one, a measure of how strong is the gravitational field. Then, how do we define this one? This one, how do we define it? How do you define this? Based on the formula, you say it is force per unit kg. Force per unit kg, right? This is the definition. Then what is this? Okay, then we move the formula. We move like this. B equals to F over IL sine theta. Okay, this one, we assume that if, okay, theta is 90, if current is 1 ampere, we set some condition. Okay, we set some condition to define it. Okay, you will see. Now, if this one is this one, this one, this one, then this one becomes force per unit length. Because this one become 1, this one is 1, then you get F over L. Okay, then we use this to define it. What is magnetic flux density? Okay, magnetic flux density is defined as force per unit length. Okay, I will write down here. Force per unit length of a long straight conductor carrying 1 ampere of current at right angle. Okay. Here in my definition, I've included all the restrictions that I set. Force per unit length of a long straight conductor carrying 1 ampere of current at right angle, 90 degrees to a uniform field. So just remember this one, then you will automatically remember this one. Here in paper 4, they always ask definition in the first question. That's 1 mark. Yeah, so that is magnetic flux density. What is it? The measure of strength. Okay, now what does this mean? Force per unit length of a long straight conductor carrying 1 ampere of current. Okay, you see how they measure the magnetic field strength. They say that, okay, if I take 1 unit length, that's 1 meter. Okay, if I take one, let's say this is 1 meter. I take 1 unit length, and then this 1 unit length has 1 ampere. Okay, 1 ampere. And I put it here in the field. How much force it experiences? I use that to measure how strong is the field. Again, right? I take 1 unit length that has 1 ampere, I put it in the field, and then I see, okay, how much force it experiences. This one experiences very much force. I say this field is very strong. I take another, I take the same wire, I put it in a different field, I put it in the other room. It experiences very little force. Then I will conclude this field is stronger than the field in the other room. How do I know? I'm using this definition to conclude, okay, to deduce here. So that is the definition of the magnetic flux density. Okay, because there are many different ways of choosing to define. You can say, if I put here, then this one travel 10 meter. I put it in other room, it travel 3 meter. Then I say this one is stronger. What are you using to measure the strength? You're using distance. Okay, so there are many quantity you can use, but here they decided they will use this one. Okay, magnetic field is a very special one. Why I say so? Because the force is not in the same plane. You see, this is the field. This is the electric current or the wire, right? The wire here. Where is your force? Here, electric current, field. The force is up, right? Going up. That means your force stick out from the plane, this is your force. This force is not in the same plane. It comes out like this. It's like, here's your wire, here's your field, and then the force is coming out like this. Okay? The wire and the field, they are on the same plane. But then the force is come out like this, okay? In front or at the back. That is the force produced by magnetic field. If you compare with gravity, is gravity like that? No, right? Gravity is follow the field. This is your Earth. That's the Earth. The gravitational field is downward like this. If you put the object here, the force is downward, follow the direction. And then they are on the same plane. If you look at electric field, electric force, here the charge plus. The field line is outward like this. If I put a positive charge, what is the force experienced by this positive charge? Same as this one, parallel to it, and then same plane as this one. But magnetic, the force is in a different dimension. It is on a different axis, on a different dimension. Okay, so that is for the force magnetic. Okay, guys, I give you a 2-minute break and then we'll cover the last part, then we will wrap up today. 2 minutes and we'll come back. Okay, right. Get one more and then we'll wrap. Okay, just now what we look at, just now we looked at if we have a wire, we have flowing charge put inside magnetic field, right? For this one, we take out the wire. We only focus on one single charge or one electron flowing in the magnetic field. So force on a moving charge. We will also observe how does the magnetic field affect the motion and the principle behind it. Okay, now we'll see. Here we have a field again. Suppose that there is a charge flowing in this direction, a charge having a charge Q, and then it is moving at a certain velocity V. Let's take a positive charge, okay? Because positive charge is the flow of current. Now, when it flows here, you have a moving charge. A moving charge will experience a magnetic force. Okay, so left-hand rule, index into the screen, the current. Now be careful with your current. No? If this is a negative, where is your current? For positive, positive is the same as current flow, right? So if the positive is going here, then your current is going right, like this. Then your force will be upward. But if I change this to electron, negative, electron has the opposite direction with current. So if electron flow here, where's current flowing? Current is going the opposite, right? So when I do my left-hand rule, index to the board, the middle finger I have to twist like this. Yeah, like this. Be careful when you twist your hand, don't sprain your hand. Okay, like this, huh? So my middle finger is left, this one is to the board, this one is downward. So if it was a negative, then the force will be downward. Okay, again, you have to look at what charge is this one. That will affect the direction of the current flow. If it's negative, you have to reverse it. If it's a positive, then you just follow it. Okay, now positive, then we have a force, right? The force is up. Velocity is going here, force is going up. The force will change the course of the motion. Here, it will be deflected like this. When the charge got deflected here, again, it is still moving in the field. So you have another force. The same force is acting like this. Again, the force deflects it. Now it is like this. Again, the force deflects it. The force is acting always perpendicular to the velocity vector. Okay? Because your left-hand rule is always perpendicular. Your force is always perpendicular. Perpendicular, perpendicular, perpendicular. All right. So again, it tries to come here. It is deflected. Here, 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 and then here. What do you get? If I make the arrow smaller, then you get a circle. That means a moving charge in a magnetic field, they are moving in circular motion. Okay, they are moving in circular motion. Force points to the same direction in the middle. Okay, so here I will change this to a circle like this. This is the velocity vector of the charge. Okay, so if your field is big enough, then the charge will eventually move in a circle. If the field is not big enough, then maybe it will only change the course. For example, if the charge come here and it experience the force, it only curves like this. Okay, it only curves like this. This is not a circle because the field is not big enough. Right? It only changed the course, but you see a part of a circle. You see a part of a circle. If I make this everywhere, then you get a circle. So this is a circle with a larger radius. This is a circle with a smaller radius. But eventually, if it is in the field, then it will move in circle. Okay? Now, here. This is the force acting on one charge, correct? Positive charge, right? Then we'll derive, okay, what is the force, the magnitude of the force acting on this charge? We already have the force just now. What is the formula? Here, F equals to BIL sine beta. This is force acting on what? Force on current carrying conductor. If I want the force on one single charge, what do I do? Okay, you have learned that the drift velocity equation, let's say this is the wire. You have current flowing I. Current can be also expressed as NEVA. This is electron density. This is charge. This is drift velocity. And this is cross-section area. Cross-section area. What is electron density? This is number of electron per unit volume. Okay, so electron density is like how many electron in 1 unit volume. If you take 1 cube, 1 unit volume, how many electron is inside? This is the N. Okay, now force on a conductor. Let's say you have force acting on this wire, F, is this one, right? If I want to derive the force acting on only one electron, what do I do? Just one. Then I will divide by the number of electrons, right? Again, I have the force acting on the wire, F. If I want the force acting on one single electron, then I will divide the force by the number of electrons inside. So, force on one electron equals to force which is this one, right? BIL sine theta. BIL sine theta. Divide by what? Divide by the number of electrons. The number of electrons can be expressed by electron density. Okay, I will make this like this. Times into area and times into length. You see, what is this to? Volume. What is this? Electron density is number of electron over volume. Right? If you take number of electron over volume times the volume, what do you get? You get number of electrons. Okay, so cross dI sine theta, we will make it 90 degrees. That means this charge, we make it 90 degrees. This charge always enter perpendicularly. Like this. Okay. This charge always enter perpendicularly. So this one become gone. All right. So last one. This one, I will continue here. B. Okay. This is force, right? Force on one electron equals to B I N A times I N A. Okay. BEV. So this force is BEV, force on one electron, assuming if it enters perpendicularly. If you want a general one, we can make it DEV sine theta. Okay, normally you will not see the V. I will use BQV. They use BQV in general. Okay, the charge BQV sine theta. Okay, this one and this one. This is the basic formula. We use this to derive this one. Okay. Now again, you have magnetic flux density, Q, the velocity, the sine angle, and then F force. Okay. What is the unit of this one? We make like this. F over QV. Magnetic flux density has a unit of Newton Coulomb ms minus 1. So this one become Newton, Coulomb minus 1, M minus 1. This one minus 1, you invert again, become normal. That is the base, the unit for magnetic flux density, or it is called as Tesla. Okay, Tesla T. Tesla T, but the base unit, you need to remember this also because this is the base unit. They will also ask this Tesla T, and this is the base unit. And sometimes they will ask you to define Tesla. They ask you, what is Tesla? How do you define Tesla? We have to define it following this one. Okay, I will write the definition on the board. If they ask you to define what is the meaning of Tesla, so we will write here. Okay. One Tesla is a field intensity generating 1 Newton per ampere. Okay, sorry. Per ampere. That means for this one, Coulomb. Okay. Wait, let me get some space here. NC minus 1, M minus 1, S. Okay, we will do one more step. We know that I equals to QT, right? So ampere is Coulomb second. So Coulomb is ampere second. And what is Coulomb minus 1? It's ampere minus 1, second minus 1. Okay. Correction. Just now, I said that this is the base It should be this one. That means this is used to define Tesla. 1 Tesla is the field intensity generating 1 Newton per ampere per meter when current flow is perpendicular. Okay, don't forget we take 90 degrees here. Right, so Tesla is the strength of the magnetic field. So just to give some perspective, what is the strength of, how many Tesla is one small bar magnet? One small bar magnet, it's about 0.01 Tesla. Okay. So usually it's a very small number. Sometimes in the question you will see milli, micro, okay, milli Tesla, micro Tesla is a small number. The Earth magnetic field also very small, 0.00005 Tesla. Earth field. Okay, so that is the for the B. So we have 2 equations so far, this one and this one. This one and this one. Okay, this one just now is the circular motion, right? That means what you learn in a circular motion. Still remember circular motion? If you take further maths, you have learned it, right? In further maths as well. Circular motion, centripetal force. What is required for it to move in circle? You must have a centripetal force. So in this case, who is the centripetal force? The magnetic force is the centripetal force. The magnetic force is the one that keeps it in circular. So it becomes the centripetal. Centripetal force F equals to mv squared over r. Okay, after we finish the chapters in the A2, I will revise again the circular motion. This one I think we have covered in the AS, but it has been some time, okay? So maybe we forgot. Now, mv squared over r, centripetal force, is the magnetic force, right? This is the magnetic. Okay, so you put magnetic inside. What is magnetic? BQV. Here. BQV. Cancel, become 1. BQ equals to mv over r. This one, V equals to BQR. This one is a very useful formula because you can make V in terms of all this. You can also make R in terms of all that. R equals to mv over BQ. You have another one. What is R? The radius of the circular motion. Okay, charge, which will not change. The field strength, also not change. Mass, also not change. All these are constant. The R and the V. It shows you the relation between the V and the R. This is the linear velocity here. Okay, V and R relation. Here again, you have another relation. This one, sometimes they will ask this. Okay, velocity, linear velocity. Now, sometimes they ask you to find what is the radius of the circular motion. Okay, you use this one. Okay, let me see if I left out anything. Yeah, I think that's it. Many of the question will come from here and here. They ask, there's many types. They will ask, okay, if I use like increase the mass, if I take 4 times the mass, then how would it affect the speed? Okay, all the algebra things. If I twice the mass, then how would it affect this one? So always remember when you use all this relation, make sure you are clear which one is the constant one. Okay, so which one is the one that is not changing? If you want to see the relation between here and here, you have to make sure these are all constant. Then only you can see the relation between this and this. Okay, right. Okay, so how many formula? This one, this one, this one, and the BIL. What? The BIL. Let's go back to okay, so we come back to this syllabus. Now, magnetic field, number 1, again. Understand that a magnetic field is an example of field force produced either by moving charges. So we have talked about this, and permanent charges, right? The field lines. And then at the bottom, you can see also sketch magnetic field pattern in a long straight wire, flat circular coil, and long solenoid. Understand that the magnetic field due to the current is increased by a ferrous core. Why and how a ferrous core can improve the strength. Understand that a force might act as a current carrying conductor placed in a magnetic field, and the calculation behind it, okay, this one, BIL sine theta. Direction also, you find it using the Fleming's left-hand rule. Make sure you know how to use the Fleming's left-hand rule. And also number 3 is define magnetic flux. How you define this one? Remember, we talked about this as the force acting per unit current per unit length on a wire placed at right angle. So this is the sentence that we have taken down just now. Force on a moving charge. Determine the direction of the force on the moving charge, and then the calculation behind. Now, Hall voltage, I did not manage to cover it in this lesson. I will cover it in the following lessons. So we will talk about Hall voltage, Hall probe. Okay, basically all what's written here. And then in the next lesson, we will also cover the induction, and then we'll go into the alternating currents and then the rest.